Okay, so today we begin this last part of the course, which is to do with the cosmology. Well, as luck would have it, we only have 6 lectures left, so we cannot do as much in detail as I had originally hoped. So my goal here is to really give you a kind of a broad overview with sufficient details and references where you can find this material. Unfortunately, this material is all over the place these days, and therefore there will be a lot of references and you can look up the details. And what I'm going to do is to concentrate on issues that you're probably, today's lecture particularly, I'll concentrate on issues that you're really familiar with, but there are always gaps. When we have qualifying exams for students, I ask elementary questions such as, please explain what is homogeneity and isotropy, and they can't do it. They just start writing down a line element. That's not homogeneous and isotropy. You know, there's a geometrical notion of what is it, how do you arrive at this metric that we have. Elementary things like that. And also I think all of you are sort of grew up in the time where modern cosmology really started about 20 years ago, 25 years ago now. And that was already kind of, you grew up with this modern cosmology and you don't have kind of there was no reason for you to know what happened before very much, but it is really good for you, all research, you know, to be aware of how the subject evolved. Not in great historical detail. It's a fascinating story. I can even give you a reference of a historian and philosopher of science, a very distinguished one, by the name Kragh, K-R-A-G-H, who has written a very nice book on cosmology, and how various things evolved and so on. But we're not going to do in all that detail. But nonetheless, I think it is important for you to understand, you know, earth-shaking things that happened. And you, as usual, we take for granted earth-shaking things because, you know, we grow up knowing about that. I mean, it's like you with the internet. And you can't imagine life without internet. But it's good to know what cosmology was and why very eminent people struggled with things. And this is really good. There are two purposes. One is really something will give an introduction to the technical material, but the second is this is something that will be helpful for you on a long range when you yourself do research. It is going to give you really important lessons as to not to trust something just because it is most the common scenario. It may completely change in time. Okay, so that's what we start. This is our third part, which is cosmology of the very early universe. And today, we're just going to do introduction. The topics that I will do is today there'll be this introduction, which will lay out the whole structure for the rest of the lectures, and then we're going to spend some time trying to understand quantum field theory in Kerr space-times. Again, we don't have enough time, so I cannot do general Kerr space-times. We'll just restrict from the beginning to cosmological space-times. And then, having understood that, we will apply it to the very early universe. And it is here that I will be a little bit fast. I will just assume the perturbation equations that everybody uses, and I'll give references where you can find this, because to derive them we just don't have enough time. We'll take a couple of lectures and we don't have enough time for that. Okay, and then we'll conclude by, with again as usual, with observations. In other words, we'll do all these theoretical calculations on the board, and what is it that people observe, how are the observations related to what we do. So that's what we'll conclude. So let's begin with the introduction. So in general relativity, there really are two types of applications. And we have been focusing on one kind, and that has to do with kind of isolated systems. So these systems are, for example, Earth, and then we can work out what the time delays are, and the redshift is, and this is how, for example, the GPS system works up here. Or we can work out the solar system. We can look at the test of general relativity within the solar system, the perihelion of Mercury, etc. Or we can look at black holes and neutron stars and their dynamics, what happens, gravitational waves. So it's all under isolated systems, and that is what we have been doing. If you, by comparison, if you look at Newtonian Newtonian gravity is all about isolated systems. It's really about the solar system, about planets and moons of Jupiter, Saturn, etc. But in general relativity, there is a second part, which is cosmology. And in cosmology, it really is not looking at one isolated system, which as an idealization, but looking at a whole universe as a whole in an idealization. So here we are not interested in the details of, with isolated systems, we're interested in a lot of details about, what happens near the black hole horizons, what happens at infinity, can we disentangle radiation from non-radiative effects, Coulombic effects from radiative effects. In cosmology, we're interested really in large-scale structure. So we're not interested in details about what is happening, so to say, microscopically, astrophysically. So there is an astrophysical domain, say about a kiloparsec. We're not interested, that is our galaxy scale. A parsec is about 3 light years, so a kiloparsec is about 300,000 light years. And we're not interested in those scales. We're interested in much larger scales, and then averaging on those in some ways on those large scales. So this is what we're now. So we're switching the first two parts of the course were about isolated systems, and now we're talking about cosmology. Now here again, you have to take a step back and see how revolutions in science really happen, right? I mean, Newton started out with his law of gravity and laws of motion, and here he is saying, if I throw this chalk, what is the trajectory following under the Earth's gravitational field? But for that, we have to know what the Earth's what are the force of the Earth's gravitational field. So you have to combine the two things. And the breathtaking leap is really to say that the moon is behaving exactly the same as a chalk. The same laws apply to the moon. The moon is really always continuously falling towards Earth, right? Because that is attraction, and so it's really so to say continuously falling towards Earth, but it has initial speed, initial velocity, and that is why it goes around. If I threw this chalk with a velocity bigger than the escape velocity, it would do the same thing. And this is a spectacular leap, and you sort of to absorb it, and you always sort of get used to just calculating this, calculating that. No, I mean, just take a deep breath and see what this really is, right? And Einstein did the same thing. Namely, he had these equations of general relativity. They came from fundamental physical, resolving the tension between special relativity and electrodynamics. He wrote down those equations. And the first thing was, of course, he knew that there was going to be bending of light, and that the bending of light was different from the Newtonian corpuscular model of light in Newtonian gravity. And then the perihelion of Mercury. And that is what he really was very, very, very happy about. These are very famous letters he wrote, for example, to Arnold Sommerfeld, the day after he actually submitted the paper, the final paper of general relativity, and in which he had worked out the perihelion of Mercury, coming out correctly. And he wrote this letter to Arnold Sommerfeld saying, last several months, where he has been working extremely hard. They were very, very tiring, but at the same time, the most rewarding also, and so on and so forth, right? So he was working up this solar system. But a year later, he realized that his theory could be applied to the universe as a whole. And this is a giant leap. That the laws that were actually cooked up, or not cooked up, but that were applied to just locally solar system can be applied as a universe as a whole. Well, how do you do it? It's very different, right? For solar system, one is looking at the sun, and one is looking at these geodesics and orbits and such things. When we are looking at the universe as a whole, you have to idealize the universe as a whole in some way, looking at only large-scale structure, not microscopic structure. And how do you do it? Well, he just assumed that the matter distribution in the universe can be really modeled as a perfect fluid, more precisely as a dust. So every galaxy, if you like, is supposed to be like a dust particle. I mean, it's just like a ridiculous approximation when you think about it, right? You need a bold leap and bold vision to make this leap. That these laws can be applicable, these equations can analyze the large-scale structure of the universe, not just what happens to the perihelion of Mercury, and that can be done in a very systematic way using these particular methods. And really, the modern cosmology was really born with general relativity. I say modern, but really cosmology was born with general relativity. If by cosmology we mean the physical universe beyond the solar system, that the systematic analysis of that. The fact that this can be actually subject to fundamental laws and the structure can be analyzed is a huge, huge leap, right? I just want to say, impress on you how big it is. And people have been interested, right? Civilizations have been interested in the origin of the universe, how did it all begin? People have been looking at stars, have been looking at charting orbits, seeing when having various theories and so on for ages. So here is an example that I just want to read to you, just half a page. And this is from 600 BC. And this is the Chronicles of Buddha. And it says, one day, Malankaputta, who was one of the disciples, who had just joined the Sangha, the Buddha's the group of monks, and he was very perturbed, and he had all these questions. And he says, one day Malankaputta got up from his afternoon meditation, went to Buddha, saluted him, and sat on one side and said, "Sir, when I was alone meditating, this thought occurred to me. There are these problems unexplained, put aside, rejected by the Blessed One. Namely, is the universe finite or infinite? Is the universe eternal or did it have a finite beginning?" And these are the questions that could finally begin to be answered with general relativity. And then the list goes on up here, all these questions about the universe. And then it says something like, these problems the Blessed One does not explain to me. This attitude does not please me. I do not appreciate it. Therefore, I decided that I will go to the Blessed One and ask him about this matter. If the Blessed One explains them to me, then I will continue to follow the order. If not, I will leave it and go away. If the Blessed One knows whether the universe is eternal, let him explain it to me. If the Blessed One does not know if the universe is not eternal, or does know that the universe is not eternal, let him say so. If the Blessed One does not know whether the universe is eternal or not eternal, then for a person who does not know, it is straightforward to say, I do not know, I do not see. It's a very beautiful thing, it goes on, and how exactly what then happened, what Buddha said, etc., but that is not physics. So what I want to impress on you is really that these questions have been with us for thousands of years. And these questions were answered by general relativity. Of course, these answers are not perfect answers. These are approximate answers. There's a limit of domain of validity that also we'll see at the very end of the course. But that is why this era that we are living is so special. General relativity answered that, but we did not know if they were correct or not, as we'll see this today. There were a lot of controversies about it. And now we finally know, because of observations that took place in the last 20-25 years, that in fact we know a large chunk of knowledge is really well established. There are things beyond that we still don't know, but there's a whole bunch of things we know, and that is what we're going to understand in this course. Okay, so let us begin. The basic assumption up here is really homogeneity and isotropy. So we got Einstein's field equations, and then we want to say that in fact the universe on a sufficiently large scale is homogeneous and isotropic. Obviously the universe is not homogeneous and isotropic here. I mean, the sun is in one direction, we don't have sun in every possible direction. So you have to average out on this megaparsec scale, which is millions of light year scale, as opposed to just a few light years or even 1,000 light year scale. Then the idea is that the universe is really, this is an assumption that on sufficiently large scale the universe is homogeneous, it means that there is no spatial place in the universe, it's homogeneous, and is isotropic, which means that there is no spatial direction in the universe. If you like, this is the grandest version of the Copernican principle, right? With Copernican principle, we sort of removed ourselves from being the center of the universe, Earth being the center of the universe. And now one is saying, no, I mean, there is no preferred place in the universe, and there is no preferred direction in the universe. That is what one is saying. But how do you translate it into mathematics? And that is not entirely trivial in general relativity, right? How do you, what do you mean by homogeneity and isotropy? Because what do you mean by space, right? This is supposed to be spatial homogeneity and isotropy, not in time. So what do you mean by space? And there is no natural notion of space in general relativity. Therefore, because space-time is a continuum and we don't have natural slicing, so therefore this actually requires, what does homogeneity and isotropy means? That is to say, our space-time, the physical space-time, now again change the notation, and I just don't put any hats. The physical space-time is just MGAB up here because we're not going to do any confounding completions. So physical space-time is said to be isotropic and homogeneous if this admits a foliation by space-like surfaces. So this is an assumption. It admits a preferred foliation by space-like surfaces. Submanifolds, space-like three-dimensional submanifolds. Such that. So first of all, you want to say, yeah.
I just have a quick question. I'm going to kind of jump ahead here. So what you end up doing here is you say like the curvature is going to end up being constant on these surfaces, and so they should be hyperbolic, spherical, or Euclidean.
That's a conclusion.
But that theorem only applies if the manifold is simply connected. So has anybody ever like done any analysis of these homogeneous and isotropic space-times when the slicing is non-simply connected?
Yeah, so people, I mean, there is work about what is the topology of space. It's not very huge amount of work, but there is work on topology of space, particularly by a French group that people look at topology. Yeah.
Okay.
So, but we'll come back. So, there's a space-like submanifold such that. So what we want to now say is that, well, on each space-like surface, we got such that the isometry group, the group generated by Killing vectors. So the space-time has some bunch of isometries. So there's going to be a group, the isometry group of this GAB maps acts simply and transitively. And so acts gives a foliation the isometry group. Sorry, I should have written this down before. It could be the whole isometric group or a subgroup. That leaves a foliation invariant. And acts on it such that and relates. I'm just trying to avoid the standard notions of simply transitivity because otherwise I don't explain them also. So since any one point on the hypersurface to any other point.
such that any two points are related by the affection of the isometry. That's what I should say. Sorry. Valid and any 2 points are related by the action of isometry. So that's what homogeneous means, because the statement is that I got some submanifold given any 2 points. There's a killing vector whose trajectory goes from one point to another. So the metric here is the same as the metric here. So there's no preferred point up here. That's what it says. And the second thing, by isometry, so this is homogeneity. So this in particular implies that the isometry group is at least 3-dimensional. The isometry group is at least 3-dimensional. And then isotropy means that no vector in the tangent space is left invariant under this. In other words, if you give me a point, then there is an isometry which leaves a point invariant and maps any one tangent vector to any other tangent vector. So let me give you the examples, these simple examples. If I just take this 2 plane, then I can just have isometry, which is x directional translations and y directional translations. Then given any point, it's related by group of isometries, because if you give me this point and this point, I can move in the y direction, and then I can move in the x direction and join them. Okay. But on the other hand, in this case, there is no point which is left invariant, because I'm just going all given any point, it goes to some other point. But if this plane is flat, then I have 2 things. I not only have this translational killing vector, but I also have rotational killing vector. Now rotations will leave each point invariant, a rotation around this point, and therefore I'm going to get a killing vector field. And that killing vector field which leaves this point invariant then acts on the tangent space at this point, because normally if this point is mapped to this point, then the tangent space at this point is mapped to the tangent space of this point. But if the point is left invariant, then the tangent space is mapped to itself. And then with rotation, we know that given any 2 vectors, there's a rotation which will map one to the other. So the second thing is that, so isotropy, no preferred direction. That means that given any point, P, there exists an tangent vectors TA1 and at P there exists an isometry that maps, that leaves invariant and maps P1A. So we have lots of killing vectors in this case, and in particular space is say 3-dimensional, then I will have translational killing fields and I will also have rotational killing fields, and therefore in general I would have, so say I got total number of killing vector fields here, the isometry group is 6. And then the statement is that if you are given any one point, then the metric at this point, and given the metric at this point, then that determines the metric at every other point, because I got action of the isometry group. So this metric is left invariant. I just lead drag it, and I'll get the metric at any one point. So the metric at a single point determines what is happening everywhere. And modulo this technical mathematical assumptions, then the statement is that this implies that we're going to take the Riemann tensor of the space-time. It is of constant curvature. So this is all of constant curvature. So this is equal to some constant. I forget now what the constant is, but scale Riemann tensor of the 3-dimensional space is constant curvature, and therefore it is of the type some R, the scalar curvature, times the metric QAC, QBD. That's the constant curvature metric up here. And then by Bianchi identities, this R is also constant. So locally, this is all fine, but there are global issues about topology. And we're assuming that the manifold is simply connected up here. That is what the standard assumption of cosmology is. And then the statement is that we get therefore three possibilities. R is positive, R is 0, and R is negative. So the sign of the scalar curvature is called K. So this is called K equal to 0, K bigger than 0 universe, K equal to 0 universe, and K less than 0 universe. It's a little bit confusing because this word K is also used sometimes for extrinsic curvature, and this is really related to the sign of the scalar curvature and not related to the extrinsic curvature. So I think you all know all this, so I'll just go a bit fast up here. And therefore, the metric, the space-time metric, can be written as minus dt squared plus some spatially homogeneous metric, constant curvature metric, so QAB times dxa dxb. So this metric is plus 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 and constant curvature. Yeah, I think that the papers on topology are written by Jean-Pierre Luminet. He is the best, the person to look at the papers on topology. And now the statement is that, so this metric is constant curvature, so we've got these three possibilities. The one that seems to be favored by the observations is really k equal to 0. I could write down the metrics, but you have seen it in your elementary classes, the three-sphere metric, the hyperbolic metric. The hyperbolic metric is a metric on the mass shell, if you like, in Minkowski space-time. The three-sphere metric is just the three-sphere up here, and then we've got the flat metric. So the observations seem to prefer k equal to 0 case. So therefore, this is equal to minus dt squared plus, you'll just get here some scale factor, which depends only on time because of homogeneity, spatial homogeneity, cannot depend on place and space, times just dx squared plus dy squared plus dz squared, or whatever coordinate system you want to use, dr squared plus r squared, d theta squared. This is the flat metric up here. So this is just flat, spatially flat. So this r up here is just 0. Now, even in the case of spatially flat metric, the topology is not obvious, right? Because it could be that in the case of the spatially flat metric, we could have just R3 topology, or I could identify, because I could just take a cube, and just identify the opposite faces. So this face is identified with this face is identified with this face, and the front is identified with back, and that gives a 3 torus. And so 3 torus topology is actually is possible in this case. Locally, the metric is exactly this. And now one can ask, observationally, what do we know? Could the topology, as I said before, k equal to 0, but spatially flat topology is preferred. I will say a little bit more about that. But then, given this k equal to 0, so spatially flat topology metric is preferred, geometry is preferred, what can we say about topology? So it could be R3 or it could be a torus. Well, obviously, if the topology was torus, but the torus had only a kiloparsec radius, then it's ruled out because you just look around you and you don't see any signatures of light coming back or anything of that sort in our galaxy. But it's very surprising that the constraints on topology are quite weak. I mean, it could be a torus whose radius is only of the order, just a little bit more than the observable universe. The radius of the observable universe. I could give you the numbers, but I think it's not. I have to specify much more detail as to what these numbers mean. So we don't know that the topology is not T3. Okay, so that's the. But I think we just most of the time we just assume it's R3, and in many times when we are doing particularly quantum theory, when we have to worry about Hilbert spaces and so on, one often just uses periodic boundary conditions so that the continuous Fourier transform is made into a Fourier series rather than a Fourier transform. So for that, one implicitly assumes a toroidal topology. You do that in class all the time in quantum field theory courses. You just put an infrared cutoff because of a reason and put in a box and then identify the opposite ends, periodic boundary conditions. And the general idea is that if the radiation is sufficiently large, then the boundary effects will go away, they will not be there, and your conclusions will be all perfectly fine. And that is really what is often done. But in practice in physics, one is implicitly assuming that the topologies are free. So the universe is actually infinite, not of finite radius, but infinite, and that the metric is just given by this metric. Now, of course, observations can never pinpoint and say that this universe is flat. Right? There's always going to be error bars. So the question is, what are the error bars around flatness? Are they more the window? Does it allow, there's a more chance of having it being this is spatially closed. The three-sphere topology is spatially closed. In other words, the space here is three-sphere, and this topology is open, R3. So spatially open. Again, one could do this identification with some discrete subgroup and get non-trivial topologies, and that's also something that the French group has looked at in some detail about what constraints do we have. The constraints are very weak and they are not very strong, even for the top T3 top. I don't mean they are weak in the sense that you can do anything. No, but a lot of things are allowed. I mean, you have to make the torus sufficiently large. These discrete identifications, you have to make them choose the discrete subgroup cleverly, but they are not ruled out by observations. Okay, so that's good. So this is the form, the metric. This is the form, the geometry up here. And now there's just one more thing about this metric, that this T here is called the proper time because so the idea up here is that we've got a R4 topology for the whole space time, and you've got this preferred slicing up here, and perpendicular to the slicing is a flow, right? The normal flow up here, unit vectors which are all perpendicular to the slicing, and the statement. So this is the vector. So the preferred direction up here is just normal to the slicing because of spatial isotropy up here. This is normal to the slicing. So this vector field is just d by dt, and this is equal to 1. Since I just have 1 up here, t is a proper time for this observer. Whose world lines are orthogonal to the homogeneous isotropic slicing up here. But then very often in cosmology, particularly when people study perturbations, one just notices that all these models, in respect to the topology, they're all conformally flat. In this case, you can see explicitly that it's conformally flat. So let me put here a bar. No, it doesn't matter. So this is conformally flat here, a squared of t times that. And therefore, what I can do is to put ds squared to be equal to, I can take s squared of t outside and put minus et squared upon a squared of t. Flat metric up here, and just define d eta to be dt. And therefore this metric then will become, and express A as a function of eta, so it will be some other function of eta times minus dt squared minus deta squared. This makes a metric manifestly conformally flat. The metric is conformally flat, this y tends to be 0, but makes it manifestly conformally flat, so this is a flat metric. But eta here is not the proper time coordinate, and therefore this eta is called the conformal time. And the literature, dot stands for d by dt, and prime stands for d by eta. seems to be pretty universal convention. Sometimes the proper time is called tau. Sometimes the conformal time is called tau. So but you just have to make sure which time you're talking about. Are you talking about proper time, or are you talking about conformal time? Okay. So this is the form of the metric in general. I just write this down because we're going to use both forms of the metric, especially in perturbation theory, we will use the confounding flat form of the metric. So this is geometry. So the idea is that we assume spatial homogeneity and isotropy and some global topological assumptions. Then the statement is that this is what we have. And as I was saying before, of course, k equal to 0 means observationally this is preferred, but there is an error bar, and we can ask which way is it bigger. And the thing is that it's more likely that the universe is actually, and if it is not exactly, k is not exactly 0, the error bars are such that it's more likely that it's likely has a positive k rather than negative k, positive scalar curvature rather than negative scalar curvature. But ironically, in the literature, you will find this case being studied much more because somehow it fits in better with string theory. Whereas this is what, if at all its k is not equal to 0, we should be really looking at this and understanding the perturbations of this. And it's very surprising because the detailed perturbation theory and observations and what the effects of finiteness of the universe and such thing, they were not actually worked out. They were worked out here 2 years ago by a student and a postdoc, Rajesh Gupta and Beatrice Bonga. It's very surprising that such basic things were not worked out. All the work has been really focused here, and some on this because it was inspired by string theory. So this has been, I don't mean there was no work here, but even the basic things like working out the effect of the finiteness on the observed spectrum were not worked out. All right. So now we want to say, so this is geometry, and now we would like to say, what about matter? In Einstein's theory, we want to look at matter, and the matter is taken to be perfect fluid. And I want to say, so that is to say, it has a form PAB is equal to rho UA UB. This is the observer photo velocity vector field. This is U dot U is equal to -1. And then plus pressure times UA UB plus GAB. And you can see that this object is exactly what we call the spatial metric QAB. Right? This is a spatial metric up here. So if you like, you can also write this as rho UAUB plus P times the spatial metric QAB. And this spatial metric QAB is the one that we have said is just flat. It's spatially flat up here. But there's a conformal factor, a squared of t down here, and therefore this is changing in time, and therefore the geometry is changing in time. Okay. So this is what is assumed. And typically when one studies this perfect fluid, one also assumes some equation of state. In order to really get the deterministic system, you have to specify some relation between pressure and density. In cosmology, the equation of state is taken to be P is equal to omega rho, and this omega is where omega is taken to be constant. There are several studies in which omega is also time dependent. In fact, that's a more realistic thing than to make it time dependent. But we're just going to do the elementary thing and just assume that omega is equal to constant. And then if omega equal to 0, then it is called dust. If omega equal to -1/3, so P equal to -1/3 rho, as you know, such perfect fluid is sort of models and a universe which is filled with radiation. And very often one does something a little bit peculiar. From conceptual point of view, one writes down Einstein's equations with a possible cosmological constant. (8 pi g times TAB). And then one moves this geometrical term to the left-hand side. So keeping this just the Einstein tensor, the Ricci tensor minus 1/2 scalar curvature times the metric. And therefore I just get here 8 pi g times now, this is going to be TAB, and let me put M here for matter. And then minus I'm going to get lambda upon 8 pi g times DAB. And so we can treat the cosmological constant as a matter term if you want, just by moving it outside, where the effective, the cosmological constant stretching tensor, if you like. You can think of this as cosmological constant stretching tensor, and that is just given by lambda upon it. Sorry, I just moved this out on this side, so it's lambda upon 8 pi g times DAB, and this term can be taken to be the cosmological constant minus lambda upon 8 pi g times g. You can think of this being the contribution of the stretching tensor due to cosmological constant. And when people talk about dark energy and so on, this is what they are doing. They are referring to this as being the right. They're referring to taking the cosmological constant and think of it as some matter field up here. And the idea is also, I mean, it's motivated because one just says that, well, it could be there's not really a constant. It could be some field which is approximately constant, and that is why it is, you know, one wants to put it up here. That's what people do up here. So, so this lambda, as you can just see up here, if lambda is equal to this, then I can write down this lambda to P of lambda AB as equal to minus 1 upon 8 pi g times, I'll write GAB, I expand out GAB, and GAB is equal to minus UAUB plus QAB. So I just put lambda inside and expand out GAB as UAUB plus QAB. And therefore, from comparing here, you see here that lambda coming from the cosmological constant, the energy density coming from the cosmological constant up here is just given by, is just given by lambda minus lambda upon 8 pi g. And the pressure coming from cosmological constant, this term up here, is just given by minus lambda upon 8 pi g. Right, with this minus sign here. And that's why one says that cosmological constant effectively has a negative pressure and has positive energy density. And so therefore here, therefore P is equal to minus rho, so omega is equal to minus 1. This is often taken to be cosmological constant. I put it in a box because of two reasons. One is that this really was a term on the left-hand side, and we're just taking it on the right-hand side and interpreting it as energy density and pressure density. But more importantly, because various formulae I'm going to write down actually break down for omega equal to minus 1. So you have to treat omega equal to minus 1 separately. So we just assume here omega is bigger than minus 1, then various formulae are true. So assume that this is true, and then plug in Einstein's equations. GAB plus lambda, GAB is equal to 8 pi g times TAB. We have these components up here. So if you like, at the moment, we just ignore lambda term up here, and we just look at the ordinary matter, look at dust and radiation case up here. And in general, the statement is that if this is the case, then Einstein's equations tell us how what the evolution is. They determine the whole system up here, and that tell us that in fact the scale factor A that we're talking about behaves in some way, and I just want to get the numerical factors correct here. Yeah. So the statement up here is that it says that A of t, there are constants. So A of t just is time dependence is given by t to the power 2 times 3 omega minus omega plus 1. And so you can see that if omega is equal to minus 1, this thing blows up, and therefore something is not working up here. It is because these expressions were obtained assuming that A of t is polynomial. If we have got a cosmological constant, then in fact A of t, the universe actually grows exponentially, and therefore it doesn't fit in this little calculation that people often do. So this is how A of t behaves, and omega and the larger density up here goes like a to the minus 3 times omega plus 1. Yeah. This actually is correct, because if omega equal minus 1, then energy density remains constant, and indeed energy density is a constant up here. So this is correct, but this is not correct. And if you, so this, I mean, if omega is equal to minus 1, even though this was obtained under assumption omega is always bigger than minus 1, the final result is correct. Here, whereas here the final result would not apply if omega is equal to minus 1. So therefore, if it is dust, then you see that A of t behaves like t to the, so for dust omega is equal to 0, so it is t to the 2/3. And then rho behaves like rho times a cube is constant, so it is omega minus 3. And here the universe expands as this is 3, not 5. This behaves like t to the 1/2, and rho behaves like a to the minus 4. So, so at first it looks sort of strange because it looks, yeah.
It should be a 1/3, not a negative 1/3 for radiation. I think it might work.
Radiation is, let's say so. So t to the 2/3 times omega is equal to minus 1/3, right? Sorry, omega equal to 1/3, okay.
Yeah,
Omega is equal to 1/3, not minus 1/3. Maybe that is what. Yeah, this was typo, not one.
Yeah.
So omega is equal to 1/3 plus 1. So therefore t is equal to 2/. So you'll get here t plus 1, that is 2/3, and therefore it is t to the 1/2. Yeah, sorry, this was this. So it's t to the 1/2, and then, yeah, the pressure is positive, there's no problem. So at first it might look a little bit counterintuitive, because it looks like the universe is expanding faster with dust than it is expanding with the radiation. But radiation has pressure, so you would say, wait a minute, I mean, what is happening here? Shouldn't it be that if there is a pressure, right, I mean, they're actually forcing the matter out, and why is it that this universe is expanding a little bit less? And that is because of Einstein's equations, which are, it's not a very profound point, but but it is a feature of Einstein's equation. And this is kind of a non-trivial feature of Einstein's equation. And the feature is the following. So you look at Einstein's equations, so GAB is equal to 8 pi g times GAB. And at the moment, let me just ignore the cosmological constant just for definiteness. So then the so this TAB is a matter TAB up here. And then the statement is, what is it that, what will Einstein's equation give? So I can take here the time components, TB component, I can take the space-time component, and I can take the space component. I can do these various projections. The time component is called the Friedmann equation. And this just tells us that a dot or a, and dot always is derivatives with the proper time, as I said before, squared. And this quantity, as you probably know, is called the Hubble parameter squared. So, of course, sometimes it's called Hubble constant, but it's not a constant, by definition it's time dependent. So when people say Hubble constant, they mean Hubble, the value of h now. It's not a constant. So this is just equal to 8 pi g. Rho. So that is the famous Friedmann equation that you get. And what it's saying is something very interesting. It is saying that a dot over a is equal to 8 pi g over 3. Therefore, if you have matter which satisfies standard energy condition, so that the energy density is positive, the TAB times some, you plug in two time-like vectors, you get something which is negative, that is the energy density is positive. Sorry, you get something that is plug two time-like vectors, so you get something that is positive. UA, UB, I plug into it, I'll get something, just a rho which is positive. So if energy density is positive, that means a dot or a could never vanish, right? So therefore, this would imply immediately that A dot over A never vanishes. If there is always, however small the energy density, the energy density is going to be decreasing, like a to the minus 3 here, so it's going to fall off quite rapidly, but it's never going to be 0. And so it never vanishes, therefore rho is bigger than 0. And that means that the universe is either expanding, that means A dot is either positive or negative, it can never change sign, either expanding or contracting. So that is what we get. This mixed equation up here, that is trivial. The reason why it is trivial is because of isotropy, homogeneity and isotropy. Because I got here TAB, QA, BC. When I project this equation then, from the geometrical part, I should be able to get a vector, a spatial vector. This is a spatial vector up here. But on the other hand, there is no preferred spatial vector. So I'll just get when I project, when I do this projection for a spatially isotropic, spatially homogeneous and isotropic metric, this term, when Einstein tensor is projected, I'll just get 0. And again, for spatially homogeneous and isotropic TAB, rho is a function only of T. Then when you substitute in here, you will find that the right hand side is 0. So you just get 0 equal to 0. And that is just because of symmetries. Homogeneity and isotropy. So this is what happens up here with homogeneous and isotropy. And what about this last equation? Where when I project the left hand side into the free surface, I get a second rank symmetric tensor, right? Because this is a second rank symmetric tensor. I project it down, I get a second rank symmetric spatial tensor. But in a spatially homogeneous and isotropic model, under those symmetries, the only second rank symmetric tensor that we can have is the metric tensor. Therefore, this object, GAB times QAC, QBD, is always proportional just to the metric QCD. It is just proportional to the metric. So instead of getting 6 equations, you just get only 1 equation. This is proportional to the metric. This is also going to be proportional to the metric. So the metric sort of cancels out, and I just get 1 scalar equation. So we get only 1 equation instead of 6. Both sides are just proportional to the spatial metric. And this equation is called the Raychaudhuri equation. And the Raychaudhuri equation says that A double dot, now acceleration comes divided by A. Those of you who know the initial value formulation of general relativity, the space component always tell you how the extrinsic curvature is evolving in time, K dot. K, this extrinsic curvature is the first derivative of the metric, and therefore K dot is the second derivative of the metric. But the metric is all contained in A, and therefore I get here second derivative over here. A double dot over A is equal to minus 4 pi G over 3 times rho plus 3p. And this is what we obtained, which is somewhat unexpected. Because you would think that only the energy density would gravitate. What this says is the pressure also gravitates. Now, if you just had this rho, you would say, oh yeah, I understand it. If I have a lot of energy density, then the acceleration, the expansion, is not going to be as fast because there is attraction, right? Gravitational attraction. So you explode a ball to begin with. So the particles, if there was no gravitational attraction, then they'll just fly out. The velocity will be conserved, the momentum will be conserved. But if you have the gravitational attraction, then of course that it will be slowed down. Therefore, the acceleration is going to be negative up here. And now what this says is that even if there is pressure, so long as the pressure is positive, in fact, pressure acts in the same way as density. So even if there is pressure, the expansion of the universe, for the expansion of the universe, pressure acts the same way as the density, and therefore it slows down. Therefore, for dust, the universe expands faster, 2/3, and for the radiation field universe, it falls only as T to the 1/2. One last kind of comment that you all know, but I think we often forget, namely that the scale factor itself does not have any meaning. This is not invariantly defined. Because the metric, remember, is equal to minus dt squared plus a squared of t times dx squared plus dy squared plus dz squared, t vector squared. If I just multiply the scale factor by alpha squared, then I can just divide the coordinates by alpha, same quantity up here, and then the metric has not changed at all. In other words, the scale factor is a metric coefficient in some coordinate system. And there is no God-given coordinate system that I can put, right? And therefore, the statement is that, because I have this rescaling freedom in the coordinates up here, and therefore the scale factor itself does not have any physical significance. However, if I take the scale factor at two different times, this is invariantly defined. So to say that scale factor is very large doesn't mean anything, but the ratio of the scale factor is very large does mean that the huge expansion took place. And in the cosmology literature, it's a convention, but people put a equal to 1 today, just by fiat. If you like, that is like fixing its coordinates here. If a is equal to 1 today, then the ratio are all fixed, because a of t1 is today is equal to 1, and then therefore when in cosmology literature, therefore, sometimes when you find the scale factor, it does have well-defined meaning, because it's assumed that that is the value of the scale factor at time t if the scale factor were equal to 1 today. So this is an implicit assumption that is often made, so I just wanted to point that out. Okay, so these are the very, very basics, and now we go on and we go on and see what happened up here. So now I would like to tell you about a brief history of cosmology. So we're just collected facts together, and then what happens about what happened in history. And this is something that you should keep in mind. So, as I mentioned to you, already in 1970, Einstein published his general relativity final paper in 1915, November of 1915, end of November of 1915. But by 1917, he had already worked out this cosmological model. So in 1917, Einstein applied to cosmology. Applied equations, general relativity equations to cosmology. Now at that time, it was completely believed by everybody that the universe is static. Because you look around us and the stars are always there and the universe is completely static. I mean, on large scale, of course, the planets are going around and so on and so forth, but on large scale, the universe is actually static up here. So Einstein therefore assumed staticity and then he found, however, that he could not find solutions to Einstein's equations under these conditions with this static staticity, because we just see here that, for example, a dot by a is equal to this, so therefore a dot is never going to be constant, right? It's always going to be. However, as we saw before, that we can put in the cosmological constant. And if I put in cosmological constant, then I would have an energy density coming from cosmological constant, but also pressure coming from cosmological constant. And therefore, the statement is that I could hope to balance, in this a double dot by a, I could hope to balance the pressure and the energy density together. So I assumed staticity, and he realized that he needed a positive cosmological constant to achieve this. So in the Right-Choudhury equation, if you have positive cosmological constant, then you get an extra term up here, and you can actually balance the two things together. I was going to do it in a little bit more detail. It was much slower than I thought. So and I think you have seen this before. So you wanted to add, so you needed to add a cosmological constant. And then he produced a solution, and the solution he produced was a closed, so this was all, I should have said that, sorry. So this is, I've written down up here the Friedman equations. So that assume lambda equal to 0 and k equal to 0. So Einstein assumed staticity, and he also assumed a three-sphere topology, closed universe, not open universe, not flat universe, but he assumed three-sphere topology. With the three-sphere topology, there's an extra term up here which comes with a negative sign, and then with the cosmological constant, then there's a positive sign from the cosmological constant, negative sign from the curvature term, from k, curvature term up here. And here, you're again also going to get corrections to these equations. But it is such that you can find a solution which is static. So topology is H3 cross R. So this is called the Einstein cylinder. So this is S3, this is R. And so the metric just looks like the metric that we wrote down before, if you like, ds squared equal to minus dt squared, plus, but there's no scale factor now, plus qab dxa dxv. And this is just a three-sphere metric. And the radius of this three-sphere metric is obtained by balancing the cosmological constant term with the curvature term up here that is given to us. So such solution was possible, and therefore he published this as a solution of Einstein's equation, and this was supposed to be the cosmological one. The same year, so this is static and it is filled with matter. It is dust filled. I'm going a little bit fast, but I think you have seen these things before, so it's okay, right? Does anybody work? Okay. And then in 1970, the same year, De Sitter found another solution. But in this case, there is no matter, but there is a positive cosmological constant also. In both cases, therefore, there is a positive cosmological constant. And this is the De Sitter solution that you all know. It's a constant curvature. Again, the topology is 3 cross R, but it's not static. I mean, there's no global time-like Killing factor field. No global time-like Killing factor field. So it's not static. Here, there's a minus dt squared is time-like Killing factor field. It's global. So he wrote down this particular metric, which I think everybody knows this is a metric, so let me not write it down. It really corresponds to just the you all know that if I take Minkowski space in any dimension, and if I look at unit space like vectors, then the trajectory, the unit space like vectors up here, this is all unit space like vector, they will give me a hyperboloid. This hyperboloid by inspection is time-like. And since the normally space-like, it has signature minus plus plus plus. If in fact I started with a 5-dimensional Minkowski space. In 5-dimensional Minkowski space, the hyperboloid is going to be 4-dimensional, and it is just defined by eta dot eta, the space-like vector is equal to plus 1. And so this is the De Sitter metric that we have up here, and the universe is sort of, if you like, coming in, it's contracting, and then going out again, it's expanding again. Now these two were the models of the universe, and it is very surprising for people to realize that, so this was obtained in 1917. 1924, Alexander Friedman in Leningrad found the solutions that we all talk about, the Friedman universe, the solutions that I talk. He solved those equations for dust, for perfect fluid, etc. And in 1926, completely independently, Lemaitre found also the solution of Einstein's equations. So these solutions were there published. When Einstein did see Friedman's paper, he did not see Lemaitre paper, he did see Friedman paper, but he just believed that, in fact, that Friedman had made a mistake, that he didn't think that he somehow, it was unnatural for Einstein to believe that there could exist solutions with a dynamical solution to his equations. He wanted a static solution because he thought the universe is static and that is what had to be explained. And so he thought that there was a mistake in Friedman's paper, and he said that. But then, soon after that, I forget the names now, but a Russian mathematician went and saw Einstein went to visit Einstein in Berlin, and sat down with him, went through the Einstein's objection and showed that Einstein in fact was wrong, that Friedman had not made a mistake. And Einstein was always very gracious about this. He immediately acknowledged that he was wrong. He told everybody he was wrong. But still he did not take this thing seriously. He said, yeah, it's true that these are mathematical solutions, they are consistent, but they are not, that's not, the universe is static and the universe is explained. And as late as 1930, Eddington, who at that time was astronomer royal and was the leading, he had already done the mission to measure the light deflection, and therefore, in 1919, and therefore it was all, he was very, very well known, and he understood general relativity very well, etc. And he was the president of the Royal Astronomical Society, and there's a very famous session in which he said, well, we had this problem, or the description of the universe. We had these two models. Einstein model has matter, which is nice, but it's static. And it's inert, nothing happens there. And De Sitter, on the other hand, he said, there's a perpetual mobile, because there's no matter in it, but the universe, so to say, starts off large, contracts, and again becomes large. So he calls it as a perpetual mobile machine that is up there. And which one should we take seriously? Should we take this seriously or this? And he sort of felt, well, no, we should add a little bit of dynamics to Einstein's equation by adding a little bit of matter to this. Sorry, we should add a little bit of dynamics to Einstein's equation by adding a little bit of matter to De Sitter universe. So as late as 1930, people were really not taking these solutions, even though they were there in the literature, seriously at all. I just want to say one more thing, that in my view, I looked at this history in some detail. In my view, Friedman did not completely understand the physics and astrophysics of these models, whereas Lemaitre understood it completely. He did understand that Big Bang was a singularity. He did understand very clearly that these particles should be thought of as galaxies. And he actually worked out the redshift formula that we attribute to Hubble. That was completely worked out by Eddington before Hubble's time up here. In 1934, around then, Hubble had been making observations, but by 1934, it became clear through those observations that the universe is actually expanding. And this is the famous year in which Einstein accepted the universe is actually expanding and said that his greatest blunder in his life. He never said that actually in German, but people attribute this as being the greatest blunder was that he put a cosmological constant, the positive cosmological constant in the solution. In fact, the cosmological constant should be 0, and everything, and then he accepted that these solutions were there. But he, as late as in the 60s, 70s, sorry, not 70s, he died in 55, not in the 60s either. In the 1945, I think around, or 1940s, he wrote this paper in which he explicitly said that, well, there is a singularity in Friedman equation, but we should not take it physical. It's just a mathematical artifact, physically something else may happen. He did not say quantum theory, but something else may happen. But still, the statement is that at the end, what we have is the solutions of Friedman and Lemaitre, which then survived after 1934. And these solutions have a dynamical, space-time is dynamical. And as you can see up here, for these matter fields that I talked about, omega equal to 0, omega equal to 1/3, for those matter fields, in fact, at t equal to 0, the radius of the universe shrinks to 0. This QAV metric up here actually goes to 0, the radius shrinks to 0. The scale factor, not radius of the universe, the scale factor shrinks to 0, and that is a genuine curvature singularity, and that was a Big Bang. And then for a very long time, there was a debate about this Big Bang, should we take it seriously, should it be not taken seriously, etc. And next time, in the first 10 minutes, I would explain what changed, and then how we are arrived at the current understanding of the universe, and then after that, we'll start doing. A key role is played by quantum field theory, which was totally unexpected until much later. In all those years, in the 70s, 80s, people didn't think quantum field theory has much to do with this at all. But it is really now that one realizes that quantum field theory in the very early universe is absolutely essential to make contact with observations. So I will explain that next time, and then we'll start doing quantum field theory. Okay.